Let's look at an example. Here we have log linear demand. Now, sometimes we have a demand function and we want to know the pricing function. That's just like finding the inverse function. So here's the question. Let's see if we can answer it. And we're going to start with part one. Part one's always a good place to start. Notice that we have log linear demand. So we got logs here. The question wants us essentially to express Q as a function of P. So it's really saying, eliminate the logs. So let's do that. And then the second part of the question is asking us to show that this identity is true. So if we've got natural logs, we want to get rid of them. Let's use the natural exponent. So I'm going to take, or I should say I'm going to raise both sides of the expression to the power of the natural exponent. The natural exponent's going to go underneath, and they're going to become exponents to the natural exponential. And so we're going to have a minus b log p like that. The left-hand side's pretty straightforward, that the left-hand side's going to be q. The right-hand side, we're not ready yet, we have to do a little bit more work. So if we're adding exponents together, that means the bases were multiplied together. So I can rewrite the right-hand side as follows. Like that. And if you want me to be very clear, I can rewrite this as like so, or maybe we don't really need those brackets there. And then the right-hand side becomes e to the a p to the power of negative b. This is kind of good. We can kind of see that we probably have the right answer. If we get a larger p, then this implies we're going to get a lower q. And if you don't see that, I could rewrite this expression like so. And then it's a little more clear that if we increase price, Q is going to fall. We're increasing the size of the denominator. So that's the first part of the question. We can put a check mark there. The second part of the question wants us to find the derivative of Q with respect to P, and it wants us to be equal something in particular. So if we're going to do that, it's easier to take the derivative of this thing here, and then I don't have to use the quotient rule. And so the derivative of this thing right there is going to give me EA. Just acts like a multiplicative constant. It's just some number. The negative b comes down from the power rule. So we've got negative b minus 1. And that's it. We've got what they asked it to do. Except that they want us to show that d of q over d of p is equal to negative b q over p. And so if I look over here, I don't really see a q, do I? But I do have a q lurking in here, and the q is from right here. If I rearrange the numerator, we can have negative b over p. P to the negative 1 is 1 over p. E a p to the negative b. And if you look closely, you can see that's what we have in the numerator. And so we're going to end up with the change in q with respect to p is going to be equal to negative b q over p. Because q is equal to EA p minus b. So we're using what we had before, and by using what we had before, we're able to answer the question. We're able to show that this identity is actually true. Now the second part of the question wants us to express p as a function of q. Notice that there's no logs there, so it's a good indication that we're supposed to get rid of the logs. So let's try and do that. Now this is what we came up with in part A, or at least the first part of part A. So let's rearrange this and solve for p. So if we want to solve for p, we could have q over EA, p negative b. And then I want to raise both sides of this expression to the power of 1 over negative b, or negative 1 over b. So maybe I'll write that out so you can see. And then we're just going to be left with p on the right-hand side. And over here, we could flip the numerator and denominator if we factor, or if we bring in that exponent negative 1. So since the next part of the question wants me to find the derivative of the price function with respect to q, I've set this up in a way that's kind of awkward to take the derivative. I could do it, but I'm going to have to use the chain rule and the quotient rule. So why don't I back up a little bit? Why don't I back up? I'm going to take this away. Let's get rid of that. And let's focus on what we have over here in terms of the left-hand side. If I bring in the negative 1 over b, I can rewrite this as q negative 1 over b times, well, super awkward, but let's go with it, 1 over EA negative 1 over b is equal to p. And if I do that, this becomes a little bit easier to take the derivative of p with respect to q, because now we can just use the power rule. And so why don't we do that? We'll take the derivative of p with respect to q, and we end up with negative 1 over b times 1 over EA negative 1 over b q, sorry, 1 over q, 1 over b minus 1. And this looks super ugly, so let's see if we can simplify this and make it better. Got negative 1 over b there. This e to the a, we've got a negative exponent, so I can write it as e, a, and then bring in the b, multiply it by 1 over b, the exponent a, multiply that by 1 over b. And then this thing over here, we've got q minus 1 over b minus 1. I can rewrite that as q negative 1 minus b over b. Whew. And we get negative 1 over b, EA over b, q negative 1 plus b over b. Now, although I've simplified this as best I could, it's actually really not helping me get to the answer of question C. So C, asks us to show that this is true, that the change in P with respect to Q is equal to 1 over the change in Q with respect to P. That's a very useful expression in economics. Taking the demand function and then finding the inverse demand function is very useful. You're going to see that a lot in second year. Now, going back to where we were, if we want to show that, I have to kind of undo some of what I've done. So let me delete a lot of what we've got down there. And let's go back to where we took the derivative of P with respect to Q. So maybe we can even do it again. And if you don't want to see it again, you can fast forward. I'm going to take the derivative of P with respect to Q. And so we're going to get the derivative of P over the derivative of Q is equal to 1 over EA negative 1 over B. That doesn't change. Negative 1 over B times Q negative 1 over B minus 1. Now we know that P is equal to, well, P is going to be equal to, I'll just write it right here, 1 over EA negative 1 over B Q negative 1 over B. And what's left is going to be negative 1 over B times Q to the negative 1. And so we're going to have P over Q times 1 over B. And I'm going to just move that negative sign into the front so it looks a little bit nicer. And so another way of writing the change in P with respect to Q is to perform this change where we recognize that P is equal to this ugly thing here. And when we see those ugly bits, we replace them. And so now we've got this nicer looking expression that says the change in P with respect to Q is just equal to negative P over Q times 1 over B. Now I did some rearranging off camera. This is our answer from part A. This is our answer from part B. And we want to show that change in P with respect to Q is equal to 1 over the change in Q with respect to P. And I'm going to take this thing then. In order to do that, I'm going to take this thing. I'm going to put a 1 over it. Or better yet, I could just write negative PQ over P and raise this thing to the power of negative 1. That's just like taking 1 and then dividing this thing. What's that going to be equal to? It's going to be equal to P over Q. One over negative B. And that is the same as our answer in part B. So we could have solved for part A, then use the inverse function theorem to find the answer to part B.